Hello and welcome. This section is about finding the shortest path between nodes in a graph. We will first look at how we define the shortest path and see some example applications. Then in the following videos we will describe and implement the Dijkstra algorithm for finding the shortest path. Let's first get started with this video to describe the problem. In this video we will first have a go at defining what the shortest path really means, and later we'll present an example problem and some practical applications. So what do we mean when we say the shortest path? Imagine a graph, like the one shown, in which one node is marked as the source and another as a destination. There are multiple paths that we can take that would make us travel from the source node to the destination. For example, we might take a path through nodes B and C, or the one going through A and C. The shortest path is the path in which the distance is a minimum. When a graph is unweighted like this one, the shortest path is defined as the one which contains the least number of edges, or hops. In this example, the shortest path is the one going through A, as it only contains 2 hops. All the other paths are longer as they contain a larger number of edges. When the graph has weights, the shortest path is the one where the sum of weights is a minimum. For example, in this path, we add 50 and 120, and we get the sum of 170. However, if we take this path, the sum of weights is only 130 kilometers. In a weighted graph, the shortest distance is not necessarily the one with the least number of edges. Our ideal algorithm for finding the shortest distance should work on a weighted graph even if the graph contains a cycle. The solution should work using a single source node and work out the shortest path to all the nodes in the graph. It's important to realize that the shortest path doesn't mean the shortest physical distance. It simply means the minimal sum of weights from source to destination. The weights on the graph can be used to represent many different properties. Let's have a look at a more concrete example so we can understand this problem better. Meet Ravi. Ravi is a student, studying and living in Mumbai. He loves traveling and visiting new places, and he is looking for a travel destination for his upcoming holidays. He has shortlisted a number of cities and other destinations. Now he just needs to find a way to get there. There are a number of ways to get to the same place. For example, to get to Colombo in Sri Lanka, he can take a direct flight, or alternatively, use a combination of train and flights to get there. He has spent some time mapping all possible transport links to get to all possible destinations. Being a student, Ravi's travel budget is tight. He doesn't mind spending more time traveling as long as he saves money. Given the choice between 2 alternative paths, he would always choose the cheapest one, even if this means that this will take him longer to get there. For example, to get to Colombo, taking the flight would cost Ravi $160. However, taking the longer route would cost Ravi only $120, saving him some money. We arrive to 120 by summing up all the weights along the path to Colombo. Ravi has collected the average cost of traveling across all destinations using various connections. He now wants to write an algorithm that calculates the minimum cost of traveling to any destination from Mumbai. The algorithm also needs to output the path of getting there, not just the cost. He can then make a decision based on the cost and how attractive the destination is. We will use this example in the following videos to build this algorithm. Finding the shortest path in a graph has applications in many other areas, not just for saving money when traveling. We are all familiar with navigation software. These applications usually model road networks as a graph and apply the shortest path algorithm to find the quickest way to arrive to your destination. Finding the shortest path has a lot of applications in computer and telephony networks, where you need to find the most efficient route through the network. Solving the shortest path problem is also the base of many important algorithms. Sometimes you can model the series of states in a problem as nodes in a graph. Changing from one state to another is then represented by an edge. If the solution is contained as a specific state, getting to that particular node in the quickest way can be solved by finding the shortest path. Finding the shortest path in a graph has many important applications. In this video we have seen a few and talked about a specific example.